look at the problem of calculating the distance on the Earth between any 2 points at the same latitude, but not necessarily at the equator. We have come across calculation of Earth distances before. The great circle distance between any 2 points on the Earth can be calculated using a general equation involving spherical trigonometry, but this is beyond the scope of the syllabus. Consequently, problems involving the calculation of great circle distances are limited to those where the 2 points lie on special great circles. These are when the points are both on the same meridian, or when they are both on the equator. Suppose we have a chart like this with a route on it. We measure the track distance with a pair of dividers. If there is no graduated scale line at the bottom of the chart, we can measure against the number of minutes of change of latitude. Can we do the same thing against the change of longitude? The answer is no, of course. 1 minute of change of longitude is not 1 nautical mile, except at the equator. Let's see why. We'll go back to some basic concepts. All meridians, along with their associated antimeridians, are great circles. However, only one parallel of latitude is, which is the equator. All other parallels of latitude are small circles. 1 nautical mile equals 1 minute on any great circle, for instance, on a meridian or at the equator. Therefore, at any latitude, 1 minute of change of latitude always equals 1 nautical mile. However, this is true only for change of latitude, or at the equator for a change in longitude. So now let's define departure and work out how to calculate it. Departure is defined as the distance between 2 meridians along a specified parallel of latitude. So departure is always a rhumb line, the parallel of latitude. It's important to understand this. There will also be a great circle distance between 2 points, which will be shorter, but this is not departure. It's also possible to calculate either the rhumb line or the great circle distance between 2 points not at the same latitude, but these are not departure either. It has to be along the parallel of latitude to meet the definition. It's usually measured in nautical miles, but it could be in kilometers. Departure will always be greatest at the equator, where it is part of the great circle. It reduces as the meridians converge, and becomes 0 at the pole, where all meridians meet. At the equator, the change of longitude in minutes is multiplied by 1. At the pole, the change of longitude in minutes is multiplied by 0. Departure is therefore a function of cosine, which has a value of 1 at 0 degrees and 0 at 90 degrees. The equation is therefore that departure equals the change of longitude in minutes multiplied by the cosine of the latitude. In the same way that we examined the sine curve when looking at convergency, let's look at some of the more common values of cosines of angles, because these frequently come up in questions on general navigation. Here is a cosine curve. Let's look at the angles between 0 and 90 degrees. The cosine of 0 degrees is 1. The cosine of 30 degrees is 0.866. The cosine of 45 degrees is 0.7071. The cosine of 60 degrees is a half, or 0.5. The cosine of 75 degrees is about a quarter, or more accurately, 0.259. And the cosine of 90 is 0. Cosine reduces from 1 to 0 as the angle increases between 0 and 90 degrees. The relationship between departure and change of longitude is therefore defined by the cosine of the latitude. This gives us the basic departure formula. Departure equals the change of longitude in minutes multiplied by the cosine of the latitude. Consider two meridians on the Earth, joined by a parallel of latitude. We can extract the basic elements of this situation in the sketch. In this example, the change of longitude is 20 degrees. Multiply by 60 to convert it into minutes. Then multiply by the cosine of 52 degrees. This gives a departure of 738.8 nautical miles.